In this segment, we're going to delve a little more deeply into the momentum representation, and, and just to summarize a little bit, and maybe introduce a little bit of different notation. We basically have found the following, that we could solve an eigenvalue problem, and here I've got the Hamiltonian operator operating on an eigenstate psi n, and that gives us the energy En, the eigenvalue corresponding to this eigenstate back again. And we found or know that these eigenstates can be made into an orthonormal basis set of that we can expand things about. Orthonormality is just this condition here with the Kronecker delta. Sometimes people write this in the following way. It's somewhat more descriptive. I usually use the psi n and En, but you can think of this as an energy eigenstate, the Hamiltonian operating on it and giving the numerical eigenvalue corresponding to that state times the state back again. And this is a little bit more generally used when energies can be either discrete, like I've got it listed here, or can be continuous. And in this case here, if I've got two different energies, this delta function, and I've got continuous states, then you get a Dirac delta function here that is essentially the continuous version of this Kronecker delta. We saw similar things with the momentum. So the momentum operator presented us with an eigenvalue problem. Really, any quantum mechanical physical observable operator one can solve its corresponding eigenvalue problem, in this case momentum, and when you solve that problem, you get the momentum eigenstates, these ket vectors, so that when I operate on them with a momentum operator, I get the value of the momentum, the eigenvalue corresponding to that eigenstate. And again, these can be made and so that they are orthonormal. Momentum is usually a continuous variable, a continuous state. It has a continuous spectrum, not discrete spectrum. The eigenvalues are discrete, are generally continuous and not discrete. And so usually you'll see this to indicate the orthonormality of these eigenstates corresponding to the momentum operator in this form here, like we do for continuous states. And similarly, you can do the position operator. Position operator, it has eigenstates, which we generally are represented by this. We can sort of snuck them in, probably. And it simply gives the value of x for that state times the state back again, and so this would be the measured value that one would get for measuring the position of this particle in the state. And then again, generally these eigenvalues are continuous, and so you've got an infinite dimensional continuous eigenstates. And so usually you would write the orthonormality condition in terms of this Dirac delta function between two different states. The whole point is, though, is that eigenstates of any Hermitian operator can form a set of basis functions that we can expand any state, and here I'm just choosing psi as a general state, can be written as a linear superposition of a complete orthonormal set of the eigenstates. Okay? So, for instance, if we happen to find it convenient or would like to expand this state psi in terms of the energy eigenfunctions, we can certainly do that. These CNs are the corresponding sort of energy components, if you will. These are the basis state vectors, ket vectors. And we know how to get the CNs. We just, if I know this state, I just do this projection to get the Cn's of this inner product of psi n with psi. So once we know these eigenstates, we can find the Cn's. And the Cn's have a very definite interpretation, right? In that their absolute magnitude squared gives us the probability that this state is in the state psi n. Again, this could be continuous, and so if I use that other representation that sometimes you see for continuum states, this sum becomes a continuous integral over all of the energies. The eigenstates we represent for the energy eigenstates is this, and these functions, psi e, well, you might write them psi e, but really I kind of like to change the variable here, and because that's pretty typical as well. So I'll probably, if I ever write this, which I probably won't, I would write it as chi-e, but it's just the projection of these energies of this original state function, this inner product, just like up above for the discrete set. You can do the same thing with the momentum eigenstates. You usually write it like this. It's continuum, so you'd have to integrate over p, so this summation becomes this integral dp over all of the eigenstates. I've got essentially what would be Cn's, but now becomes a function of phi of p. And again, just like we get the Cn's up here by taking one of these as a bra vector and inner producting with psi to get this, that gives us the Cn's. And we can do likewise here to get this phi. It's just the inner product of the bra momentum eigenstate with the state that we're expanding. And likewise in position. We've already done this, actually. The state psi, integral dx, it's a sum again over their components. And this is essentially the basis vector. So I kind of think of these as like the I hat, j hat, k hat. And these are like the components, x, y, and z that go with each one of them. And again, we can get this particular expansion coefficient corresponding to the analogous thing in terms of the energy operators. And it's just the projection of the bra vector on our original state. So if you give me this state, and I can take this scalar product, and that's what we generally represent as psi of x, and I think we've done this before as well. We can get some interpretations of all these quantities, and particularly the phi and the chi up here, if you like. And it has pretty much the same thing as the probability interpretation before. The only difference is if I square this magnitude, if I square this function of p, absolute modulus squared, and integrate it over dp from p1 to p2, then that gives me the probability of measuring p between p1 and p2. So if I make lots of measurements and find of the momentum, then I find it between there. So this is like a momentum probability. You could have done the same thing energetically up here, again using this chi representation, and interpret this integral of chi squared dE from E1 to E2 as the probability of measuring the energy between E1 and E2. And so this is sort of like an energy probability function. We've actually done that. Usually we just did it discrete-wise. We usually just asked, well, what for the energy, we looked at it in this form, what was the probability of, say, energy being in the eigenstate 2? And then we were looking for this expansion coefficient, C2 in that case. And if you took the absolute modulus of it, then that's just the probability. But I could certainly take a range up here. What's the probability, once I know the CNs, finding the energy between E5 and E6, or E10, let's say, E5 to E10. Well, I would just sum the absolute moduluses squared of these CNs from 5 to 10 in that case. Well, I kind of purposefully left off the fact that I'm not really saying that this is the wave function. This could just be any state up here. So this is any quantum state. And in that regard, since I can expand any state on one of these bases sets, then I can do things like this, right? I can represent this momentum eigenfunction in terms of its projections. Okay? And the way I look at these is the following: is that I think of this as those coefficients, and we've done this before. If you look at that, that was x and p. So this is the projection on x of this operator p. And the way I look at it is I want to get a basis set, so I have this sum over this this outer product operating on this set here. So I operate both sides with this sum. And then this, we recognize I've just inserted the identity operator. Okay? We've done that before as well. So let's do things like that. Think of this as, now I can think of this as really any state, but in particular now I'm going to be thinking of this as really the wave function psi of x. And I know that it is, as we've seen earlier, is just x interproducted with the state psi. Okay? And then I separate these out a little bit and then inject the identity operator. But the identity operator is the sum over states, and I'll use this over the p states of this outer product of p with itself, summed over all of them. I then get this value here, x on the first. I take the dp all the way out. It only controls these two, so I can pull it all the way outside. This integral says integrate over all p, everything to the right. And as I have x p, inner product, and p psi. But remember, this p psi was just what we call the momentum wave function up here. That was in this representation. It's simply the representation in of the momentum of the wave function now in terms of momentum, as a function of momentum. So we get that. So psi is equal to this. Psi of x is. So we've got a relationship between the wave function in coordinate space and the momentum wave function, if you will, in the momentum space. Really, they're coordinates, quantum mechanically. But the question is, what is this this function, this inner product of x and p? Well, it turns out you can solve for that, actually. And I can start with the eigenvalue of this momentum operator. That's what we mean by this eigenstate with the eigenvalue. And it's the operator p. Operate on the eigenstate gives me a number, the eigenvalue back times that same state. And I can just come into this side with a bra vector. If I do a bra vector inner product this side, inner product this side, p is just a number, so it just goes right over to this one. And I get this. And then again, I separate this out a little bit and put in the identity operator in between. But the identity operator can be represented as this sum over states, sum over all these dx's, the outer product of x prime. And I used x prime here because I need to sum over it. And I don't want to get it confused with these x's that are not summed over. And then expand that out again. The sum is this integral is only over these, so I can pull it all the way outside, and then I get xp x prime, and then I get x prime p here, and then I have to integrate over all this stuff. However, we've already represented this operator here. This is the it should be p hat, so this is an operator at this point. So this operator here, we have represented that as a direct delta function, x prime minus x, h bar over I, partial with respect to x prime. It's really the momentum operator represented in the coordinates x. And this one I'll leave the same. So I would use that we've used before for the operator expression. And then I can do this integral because I've got this nice direct delta function. Integral of a delta function just says everywhere a thing is integrated in, substitute for x prime, and this x prime integration I substitute everywhere an x prime is, I just substitute x. And so this whole expression just becomes substituting x for x prime for x for x prime, h bar over I, x prime goes to x prime goes to x of this expression. And now I've got the same quantities on both sides. And I've got a little equation. P on this side is simply the eigenvalue, so it's a constant number. And I've got a little differential equation I can solve for this bracket term. And the way you do that, again, is separation of variables. You divide both sides by this, and then take the I and h bar over to the other side. Again, this is just a constant now. And then one recognizes that that is just the derivative of the natural log of that quantity. And now then I've got something I can integrate both sides with respect to x. The indefinite integral of this derivative of this natural log just becomes the natural log, and the integral of the integral of this derivative just becomes the natural log, and the integral of this side, well, these are all constants, so it's just IPX, and then I have to add a integration constant, which is convenient to choose in this form. There's different normalizations on these. I'm going to take a normalization for this constant a to just be 1 over the square root of 2 pi. Again, we can normalize, choose our normalization however we like, and then ultimately if it's not normalized I can choose a different factor here, but for the time being let's choose a to be this 1 over square. It's just a constant, and I could leave it until the end, but it's convenient to put it in this form now. So I found that bracket term, and so now then I can write, the whole idea was we had this expression up here that psi was equal to this bracket term times the momentum piece, function, and I needed to find what that was. Let's now plug it back in. So there's our expression, and then I plug it back in. Our solution up here just becomes this. And I get a relationship between the momentum wave function and the coordinate wave function. It's just this this integration. What about the phi p? I could do something similar for it. again, by definition, this was the that function, the bracket of p with this psi. I separate them out a bit, put the identity operator in between, but this time I write the identity operator as the integral over x, the outer product of x, x. And then again, I can pull this sum all outside everything. And then I get the px bracket and x psi bracket. This one we know, it's just psi of x. And now I've got a bracket px. So what does that equal to? Well, we've already got x bracket xp, and we know that if I take it's just a complex number. If I take the complex conjugate of it, then that's like switching the order of these two. So that was a general property of this inner product. And so for us, this px bracket is just xp complex conjugate, and so it's the same thing, it's just I've got a minus sign up here. And so plugging that in, I get phi of p is this 1 over square root times psi back again, this integral of psi over dx. So I've got this this pair, really. If you give me the momentum wave function, or the momentum representation of the wave function, I can get the wave function, or if you give me the wave function, I can get the momentum. This should look very familiar to you in a lot of ways. Notice if we let the p equals h bar k, and k equals p over h bar, and plug those in, I get this expression. And then if I just define the function phi of k over h bar times the square root as f of k, and psi over the square root is f of x, then I've got the Fourier representation, complex Fourier representation of a function f of x, where big F of k is the Fourier transform of f of x. So, kind of an interesting thing is that the momentum representation and the energy representation, psi of x, is the one we've been looking at, the regular position function. I've got really just one quantum mechanical state, namely the psi ket, and I'm representing it in two different ways. One as in terms of its momentum components, and the other one in terms of its position components, and that leads us to the psi of x and the momentum, the wave function, as it's called, and the momentum wave function. They have exactly the same amount of information on them. They're just expanding the state function on different bases. And in fact, that's precisely what the Fourier transforms do. We can view a function as being represented by f of x, or we could represent it by its Fourier transform. Same amount of information, you can go back and forth. Sometimes one's easier to use than the other. Sometimes another one is or another representation is better. But these a very broad view, at least from a quantum mechanical standpoint, really gave a solid interpretation of Fourier transforms as these position, wave function representation, and momentum representation, analogs anyway.